Okay, welcome back for the next topic. Our topic now is application of spectroscopic methods for solving scientific problems. Okay, so at which fields we are applying these techniques? What are the different fields and for what purpose? For what purpose? So that's what we are going to see here. Chemical applications. Chemical applications. That means wherever we are doing chemical research. Chemical research. So there is a chance, there is a point, there is a stage of your research where you need to identify the compounds. Identify the compounds. For example, you did some extraction. After extraction, you got crude extract. After crude extract, you separated them. So you got maybe 1, 2, 3, 4, 10 compounds after separation. After separation, you got 10 compounds. Now you want to know what is the each compound. What is the each compound? This is what we are doing in natural product research. Natural product research. When you want to know what is each compound, you need to analyze by using UV visible spectrometer, which will give you some information about conjugation. You need to analyze by using IR spectrometer, which will give you some information about functional group information, and you need to analyze by using NMR spectrometer. NMR spectrometer will give you the basic skeleton of the structure. Okay. And mass spectrometer will give you mass fragments. Fragments means small portions of the compound. Then it is very useful for building the structure of an unknown compound. After knowing the structure of an unknown compound, then only you will be able to know, yes, this is new or this is existing compound. If it is new compound, it will be very nice. That means you invented a new compound from the natural materials. Okay, so identification of unknown compounds, determination of molecular structure, functional group analysis, particularly by IR, purity and quality testing, particularly in pharmaceutical industry, we need to know about the purity of the compound, the active ingredient, purity of the active ingredient, because there should not be any side effects. When you are taking medicine, there should not be any side effects. That means your drug molecule must be pure. It must be pure. And also reaction monitoring. For example, if you are doing synthesis of a particular compound. Okay? Synthesis. So in the synthesis, usually so there are steps. A gives A gives B gives C gives D gives E. These are steps. First step, second step, third step, fourth step. That means this is 4-step synthesis. Okay? I think in organic chemistry you are studying some named reactions. Benzoylation, acetylation, okay? So nitration. So you are doing these kind of things. In one step, okay, you are doing acetylation, and then you are attaching amine group to acetyl group, okay? Something like this you are making step by step synthesis. When you are doing this step by step synthesis, that means your target is E, your precursor is A. Your precursor, the starting molecule is A, your target is E. You cannot get E directly from A. That means from A you need to get B. That means you are attaching some group. Okay. And in C you are attaching, you are modifying attaching group. Okay. And then to D, and then finally you are getting your targeted product. Okay. So now at every stage of the reaction process you need to analyze. You need to collect some part of B to analyze and confirm. And confirm, are you going in a right route or not? Are you achieved B, which is your according to your scheme? According to your scheme. Because for synthesis there is a scheme. Okay, from A I want to get this B. Already you know what is that B. Okay. Now you have to confirm whether you achieve your B or not. Okay. After achieving B, you need to achieve C. And then, so reaction progress in the synthesis is very, very important. Okay. So when you are inventing new molecules, new organic compounds can be invented either by synthesis or by natural product. These are two different research areas in organic chemistry. Okay, where we are using all these spectroscopic techniques in order to confirm at every stage. Okay, so confirmation is needed. Reaction monitoring can be done by using spectroscopic techniques. Quantitative chemical analysis. We can analyze the chemicals quantitatively by using spectroscopic techniques, particularly UV visible. UV visible spectroscopy is highly useful for quantitative analysis. Okay, so like this we have a lot of chemical applications. I kept here some spectrums. So this is wave number centimeter inverse versus percentage transmittance. That means what are these peaks? The inverted peaks. This is IR spectrum. And here the absorption spectra of benzene, naphthalene and anthracene. There are different spectra here. This is UV visible absorption spectrum. And here I kept something like a table. It is not maximizing, I don't know. So anyhow, this is the table for chemical shift. These are chemical shift. Is it right? No, it is not right. Chemical shift positions. This is NMR data. In NMR, we are getting a data called as chemical shift positions. And this is the such kind of data. Have a look here. These are different types of protons, and these are chemical shift positions. This is this scale is, you can see here. This is delta scale. This is delta scale. It is in ppm, and here you are having 0 up to 12, a scale from 0 up to 12, and here there are different protons giving peaks at different positions. Different types of protons. For example, we have OH, we have NH. Okay. This is also proton, but this is OH proton and this is NH proton. The behavior of different types of protons are different according to NMR. Okay? According to NMR, the proton is whether it is attached to C, whether it is attached to O, or is it attached to N, that matters. For example, CH. This is also H, this is also H, this is also H. But their chemical environments are different. Chemical environments are different. For this H, chemical environment is O. For this H, N. For this H, C. So the protons are differentiated based on their chemical environments. Protons having different chemical environments are behaving differently and they will give different peaks. Different peaks. Here you can see CH3 peak in this range, CH2 this range, CH in this range. This is vinylic group for which the CH3 attached. It is at this point. So like this, there are chemical shift position. This is NMR data. Similarly, we have also IR data. IR data will be very big IR frequencies, very big data. Okay. So this way, UV visible, IR, NMR, mass. These four spectroscopies are highly useful for organic research, particularly for organic chemistry research. Whether you are doing synthesis or natural product research, you need to confirm your product, your final product. In order to confirm your final product, characterization is needed. Characterization. In order to characterize, you must use all the spectrum, not a single technique, all of them, because each technique will give each information about the compound. UV visible absorption spectroscopy, IR spectroscopy, NMR and mass. These four techniques. That means when you want to characterize a particular compound, you need to collect all these spectra. I have UV visible, IR, NMR, mass. Then what you need to do is, you need to start interpreting. Each spectra will give each information about the compound. And you can build the structure of an unknown compound by using these spectra. That is called structure elucidation. Structure elucidation can be done by using these techniques. UV visible will give you some information about conjugation in the compound. IR will give you information about functional groups. NMR will give you a basic skeleton, the backbone of the carbon chain. And accordingly, you need to attach the functional groups which are confirmed by the IR. Okay, and then mass will give you fragmentation patterns which will confirm the established structure, whether it is right or wrong. So you are gathering information from different spectra to build the structure of an unknown compound. If you have only one spectrum, useless. You will get a single information. So establishment of a structure involves interpretation of different spectra. Okay. So when you want to establish a structure of an unknown compound, you need to get all the spectra, UV visible spectrum, IR spectrum, NMR spectrum and mass spectrum. Then only you can develop the structure. So, is it clear? So, examples you can see. IR spectroscope detects cardinal groups in organic molecules. NMR, as an example I kept. NMR distinguishes isomers with identical formula. Same formula but different isomers. Those can be distinguished also by using NMR spectroscopy. Okay? And we have biological and medical uses. Biological. So these techniques not only useful for chemists, but these are also useful for biologists and medical practitioners. Okay, for them also it is needed. So protein and DNA analysis, enzyme reaction monitoring, medical imaging techniques. Medical imaging techniques. For example, you can see MRI, magnetic resonance imaging, is based on NMR principles. Images of soft tissues. Okay. So medical imaging techniques. This is diagnosis support, drug interaction studies, biomolecular structure determination. For all these, for example, you see here, this is wavelength versus absorbance. That means what kind of spectrum is this? This is UV visible spectrum, and here you can see different peaks are for different drugs. So here also it is also same for different drugs. Here also same drug, but here maybe this is because it is having the same lambda maximum, same drug but different concentrations. As the peak intensity increasing, concentration also increasing. That means among all these, this one is highest concentration. So this is also useful for quantification. Okay. So for example, this is a NMR spectrometer. NMR. So here in this case, there is magnet, and this is the sample, and there is magnetic controller, and there is detector. This is RF transmitter. This means radio wave frequency. RF means radio wave frequency. This is the radiation which is going to sample, and you are getting peaks like this. This is NMR spectrometer, and in the NMR spectrometer we are getting NMR spectrum. We can generate many NMR spectra and convert that into an image. That is MRI. MRI is a digital image. It is a image. It is produced from capturing millions of NMR spectra. And millions of NMR spectra collected and then generated image. That is what it is doing. Magnetic resonance imaging, MRI. Of course, for scanning, for example, if there is some accident, something happened, if there is some swelling here, usually doctor will recommend go and take the X-ray. By seeing X-ray, you can get the information about your bones situation. Bone is okay or not? Is there any break in the bone or not? That can be. Bone is a hard tissue. Bone is very hard, but this flesh is soft. Okay, bone is hard. For the study of bones, like hard tissues, you have X-ray. But in order to study the defect in the soft tissue, the only technique what we have is MRI, magnetic resonance imaging. Because soft tissue is transparent for X-ray. You cannot get any information about soft tissue. For example, if someone goes to the hospital with some problem in the head, okay, so the doctor may be expecting maybe brain hemorrhage or brain tumor, and the brain is a soft tissue. So he will not recommend you to go for X-ray. He will recommend you to go for MRI, because he wants to see something. Is there any defect or any problem in the brain? So that can be done by using magnetic resonance imaging. Okay. So for example, UV visible spectroscopy measures DNA concentration. You can see concentration. As the concentration increases, the peak intensity increases. That means more absorbance. More concentration, more absorbance. According to B. Lambert's law, absorbance is directly proportional to concentration. Okay? And fluorescence spectroscopy tracks protein folding. And fluorescence spectroscopy is not all fluorescence. There is fluorescence spectroscopy, but of course it is not present in your curriculum content. There are two techniques called as photoluminescence techniques. Photoluminescence techniques. One of them is fluorescence spectroscopy, that is spectrofluorimeter. Spectrofluorimeter. There is another technique is called as spectrophosphorymeter. And these two techniques are highly useful in biology, biotechnology, and also forensic. In forensic also, this fluorescence spectroscopy is very important technique. For example, you might be hearing about Olympics. It is a very big sport event. So when the players are participating in the sport, in those kind of sport events, like Olympics, Asian Games, African Games, and World Cup, Football World Cup, Cricket World Cup, they will collect the blood samples from the players before the sport. They will collect blood samples from the players and analyze for any drug residues. Sometimes the players will take some drugs. When they take the drug, there will be lot of stimulation, and they will be performing very well because of the drug. Okay? Actually, it is a crime. So to avoid these kind of things, usually they collect the sample from every player and analyze by using this instrument, particularly fluorescence spectroscopy and phosphorescence spectroscopy. So because this fluorescence and phosphorescence spectroscopy, they can identify even a single molecule present in blood. Single molecule, not molar. If you say 1 molar means 6.023 times 10 power 23 number of molecules. But I am talking about a single molecule. Single drug molecule present in the blood sample can also be identified. That much sensitive techniques. Fluorescence spectroscopy, phosphorescence spectroscopy. These are useful for analyzing such drugs which are present in very, very low concentration. And that is called as doping test. These instruments are useful for doping test in the sport events. Okay? So drug interaction study, biomolecular structure determination, and so on. And these material science applications also. When you are doing material science research, these days nano science or nanomaterials are very popular. So in the material science, we can determine crystal structure, nanomaterial characterization, surface property analysis, defect and impurity detection, semiconductor band gap study, phase identification. All these can be done. See, for example, Raman spectroscopy identifies graphene. Graphene can be studied by using Raman spectroscopy. X-ray spectroscopy determines crystal structure. Optical spectroscopy studies band gaps. Optical spectroscopy means it is UV visible. X-ray crystal structure. For example, X-ray diffractometry. I already told you. Crystallographic study. Raman spectroscopy identifies graphene. As an example. So like this, you can see this is the graphene peaks. Raman shift intensity. So and the crystal structures. Okay. This is the just instrument design I am showing you. Environmental applications. Environmental pollution is a global problem. It is a global problem. Environmental pollution. So now I have an application to measure the pollution levels. I will show you later after finishing the class. Remind me. Okay? I will show you also how the pollution is at different places. Now what is the pollution level in Dar es Salaam? What is the pollution level in Dodoma, where we are standing here? Okay? I will show you. I have something to show you there. Okay? So in order to know about the pollution, there must be a pollution monitoring. And after monitoring, we need to try to control the pollution. So pollution monitoring and controlling is very important task for us in order to safeguard our health. Because of pollution problems, there are many health problems to the human beings. Not only human beings, even for many living organisms, insects, small birds, they are being affected by this pollution. Okay? So, air pollution monitoring, water quality assessment, greenhouse gas detection, atmospheric studies, climate change research, remote sensing applications. In all these, we are using these spectroscopic techniques for pollution monitoring and controlling. Because this climate change depends on pollution. Climate change depends on pollution. Remote sensing application also we are using the spectroscopic techniques. And we are using, see, this kind of spectroscopic. This is the Earth. And here there is a satellite which is scanning the Earth for pollution monitoring. In the way how you are having Google Map. In the Google Map you can see all the Earth, isn't it? Google Maps or Google Earth you can see. In the similar fashion, there is one or two satellites which are continuously monitoring the pollution levels, global pollution levels. It is also by spectroscopy. Okay. So UV spectroscopy measures ozone levels. IR spectroscopy detects greenhouse gases like CO2, CH4. Satellite spectroscopy monitor pollution globally. You can see satellite spectroscopy, isn't it? So this is how we are using in environmental applications. Now we are coming to the last one, astronomical applications. Element identification in stars. So these days, the people are sending satellites to, not satellites, rockets to other planets. After going there, a rover will come out. There is a rover which will come out. Last time India made moon landing. Our rocket landed on the moon. After landing on the moon, a rover came out. It's a robotic setup, and it identified what elements are present on the moon. Okay, there we are using this spectroscopic techniques. Okay, so element identification in stars, temperature measurement of stars, velocity from Doppler shift, galaxy composition analysis, redshift measurement, universe expansion studies. All these can be used. In all these studies, somewhere we are using interaction of radiation with the matter. Interaction of radiation with the matter, which we are saying that as spectroscopy. Okay. See, for example, I kept some examples here. Emission spectra reveal stellar elements. Redshift analysis supports expanding and universe models. Okay? Absorption and emission spectrum of different elements. These are different elements: oxygen, hydrogen, nitrogen, sodium. Hydrogen I already showed you in the first chapter. I showed you. Okay. So industrial, forensic, similar, different. Quality control testing, process monitoring, explosive substance identification, drug and poison detection, art and artifact authentication, failure analysis. Okay? Without the spectroscopic instrument, the forensic department cannot work anything. Okay? In all the forensic, forensic study involves police and the scientist. Combination of these two. Okay? So the basic is fingerprint testing, and on the crime scene, there may be some blood samples, there may be some hair of the criminal may be there. Okay? Hair sample analysis, blood sample analysis, gun residue analysis, gunpowder analysis. Okay? So like that, there are different analysis associated with forensic investigation. Okay? That's why in every country we have forensic labs. In forensic labs, what we have? These spectroscopic instruments. Okay? See, for example, IR spectroscopy checks drug formulation consistency. Raman spectroscopy identifies explosives or narcotics. Spectroscopic techniques in pharma, UV, IR and NMR like this, and we have the spectra like this, and these are the kind of instruments we have. What are the advantages of spectroscopic techniques compared to other techniques? Spectroscopic techniques are non-destructive. That is the advantage for us. During analysis, it will not destroy your sample. Sample will remain same during the analysis. And very fast, rapid analysis, high sensitivity, wide range applications, accurate qualitative results, precise quantitative analysis. Okay? These are the advantages of spectroscopy. And conclusion: spectroscopy is essential modern analytical tools, solves complex scientific problems, used across disciplines. That means the same spectroscopy can be used for chemistry purpose, geology, biotechnology, biology, biochemistry. Okay, many disciplines we are using this spectroscopic technique. These are the modern tools. Improves research accuracy, supports technological developments, and vital in scientific progress. With this, we are done. Shortcomings. Instead of saying shortcomings of spectroscopy, I can say that it is for individual technique. Where it is recording. I didn't adjust. It is recording, I don't know. First remove this. Well, let us remove this one. Right. It is still recording.